All right, so in this video, we're going to take a look at the selection sort algorithm. Now, this algorithm divides the array into sorted and unsorted partitions, just like bubble sort does. And what we do is we traverse the array and we look for the largest element in the unsorted partition. And when we find it, we swap it with the last element in the unsorted partition. And at that point, that swapped element will be in its correct sorted position. And so just like with bubble sort, at the beginning of the algorithm, the entire array is unsorted. So the last unsorted index is 6. And just like with bubble sort, we're going to grow the sorted partition from right to left. We're going to initialize a largest field to 0. So when we start, we say, you know what, 20 is the largest element that we know about so far. So whatever's at position 0 will be the largest element. And we're going to start by comparing the element at position 1 to whatever's at position 0. So we're going to start with I equal to 1. We're going to use I to traverse the unsorted partition and find the largest element. And so these are our initial values. The last unsorted index is 6 because the entire array is unsorted. I is 1. We're going to start our traversal here, and we've initialized the largest. Largest will contain the index of the largest element in the unsorted partition. That's initialized to 0. So we're going to compare 35 to 20, and we're going to say, hey, 35 is larger than 20, and because of that, we're going to change largest to 1, and then we're going to increment I to 2. And we're going to compare minus 15 to the largest element, which is now at position 1, and we're going to say, well, minus 15 is less than 35, so we're just going to increment I to 3. We're going to compare 7 to the largest element, which is still at position 1. 7 is less than 35, so we just increment I to 4. We're now going to compare 55 to 35, and 55 is greater than 35, so at this point we're going to change largest to 4, because the largest element we found so far in the unsorted partition is at index 4, and we increment I to 5. We compare 1 to 55. Well, 1 is less than 55, so we just increment I to 6. We compare minus 22 to 55. Minus 22 is less than 55, so we don't do anything. And at this point, I is equal to the last unsorted index, and so we have completed our first traversal of the array. So we're going to swap the largest element that we found in the unsorted partition, and that's at position 4. With the last element in the unsorted partition, and that's at position 6. So what we're going to do is swap 55 and minus 22. And we have now completed our first traversal, and at this point 55 is in its correct sorted position, and so we're going to decrement last unsorted index to 5. And we're going to reinitialize I to 1, and we're going to say the largest element in the unsorted partition is at position 0. And we repeat the process. So we're going to compare 35 against 20. 35 is greater than 20, so we're going to set largest to 1. Now we increment I to 2, and we compare minus 15 against 35, because 35 is now the largest element. Minus 15 is less than 35, so we just increment I to 3. 7 is less than 35, so we just increment I to 4. Minus 22 is less than 35, so we just increment I to 5. And of course, 1 is less than 35, and at this point, I equals the last unsorted index, so we have completed our second traversal of the array. And what we want to do at this point is swap the largest element, which is at position 1, with the last element in the unsorted partition, which is at index 5. And so we're going to swap 35 and 1. And at this point, 35 and 55 are in their correct sorted positions, and we decrement the last unsorted index, and so now the last unsorted index of the unsorted partition is 4. And we would reinitialize largest to 0, and that should be a 1. We should reinitialize I to 1. And we're just going to repeat the process. You know, we're going to compare a 1 to 20, largest is going to remain 0, etc., until the entire array is sorted. And so this is how selection sort works, and it's called selection sort because on each traversal, we're selecting the largest element and we're moving it into the sorted partition. So selection sort is an in-place algorithm. It doesn't use any extra memory. As I said with bubble sort, it's okay to use a few extra fields as long as the extra memory you're using doesn't depend on the number of items you're sorting. It's an in-place algorithm. It's a quadratic algorithm, so it has a time complexity of O to the n squared because we have n elements in the array, and for each element, we traverse n elements. So it's quadratic. However, it doesn't require as much swapping as bubble sort. You'll notice that we only swap once per traversal. And so selection sort will usually perform better than bubble sort. I say usually because depending on, you might have an array that's almost sorted, and so bubble sort doesn't have to swap that much. But in the average case, all other things being equal, generally selection sort will perform better. However, selection sort is an unstable algorithm. And you can see why, right? Because if we have duplicate elements, there's no guarantee that their original order relative to each other will be preserved. Because on each pass, we swap the largest element with whatever is occupying the last position in the unsorted partition. And so it's very possible that we could take the second duplicate value and move it in front of its twin. So because of that, selection sort is an unstable algorithm. So if you need a stable sort algorithm, then you don't want to be using selection sort. Okay, so that's it for the theory. Let's move on and implement selection sort. I'll see you in the next video.